Good morning, everybody. We're to keep chugging along with chapter 21. We're going to start on some alkylation reactions, which are pretty straightforward. So we are still using our enolate chemistry. If we take some sort of aldehyde or ketone, throw in a base. I'm going to throw in LDA. Followed by an alkyl halide. So in our first step, LDA can deprotonate one of these alpha positions. And then from here, we can do an alkylation where we attack bromine, or attack the carbon attached to bromine, do an SN2 like reaction to get a carbon addition. Depending on what you have, you can either use large or small base chemistry. So if we do this with a less symmetric molecule, throwing in LDA, being our large base, I'm just going to selectively pull off from our less substituted position, leading to an alkylation on that alpha position. We're adding 3 carbons. Versus if we used a small base, it's going to let us pull off this other alpha proton, leading to alkylation at a different position. So kind of your normal large, small base rules apply. All right, so some different ways to make carboxylic acids. We've talked about how to make them with one carbon additions as well as no carbon additions. So if we take I don't know, propylbromide here, we could throw in NaOH. It's going to do an SN2, make propanol, and then we could throw in chromic acid. In order to make propanoic acid. We could do the Grignard version of this. This is going to have a 1 carbon addition. Really Grignard. So adding in magnesium. Followed by CO2 and water. This gives us butanoic acid. There's a third one of these that we can do. That'll give us an even more extended system. So if we take our propyl bromide here, we're going to throw in malonic ester. Followed by H3O plus. And we're going to go through this in a minute. We're going to be able to generate pentanoic acid, so a 5-carbon version of this. So 0 carbon addition. With our CO2 or our nitrile followed by H3O plus. What's that? 1 carbon. For a malonic acid synthesis, we're going to be able to add 2 carbons. All right, so let's talk through this. We are going to take diethyl malonate. Doesn't really need to be ethyl. But that's what your book likes to use. If we throw in NaOET, we're going to pull off one of these 2 alpha protons here. They are pretty acidic because they got carbonyls on both sides. From here, if we add in our propyl bromide, bromopropane, we are going to make the general structure of our final product. So our final product is roughly this here. From this point, we're going to do what's called a decarboxylation. And we're not going to go that much into the mechanism of this. The first step is going to be where we had an H3O plus. So H3O plus will hydrolyze off the esters to carboxylic acids. And then because this is so stable, when we heat it, we're going to have what's called a tautomerization happen. I'm going to redraw this so I can do the tautomerization. I guess we're going to have decarboxylation. Nah. So we'll have something in solution, pull off, probably water. We're an H3O plus, but if you heat it up enough, you start getting different combinations of things. So with heat, you'll have some amount of water in there. It's not negative. It's going to cause you to form CO2, break down to this to here. And usually you have to heat these up pretty hot to get this to go. And then your last step, you'll just pick up the H you just lost. And we get the product of our malonic malonic ester synthesis. I'm gonna give you guys a minute to finish writing this down, and then we'll do kind of like a full walkthrough of what this looks like. So generally we use malonic or diethyl malonate as the reagent. Or I guess it's the substituent? No, it's the on this side of the equation. React. That's it. As a reactant, and then we'll add in our alkyl halide as our reagent. That's what I want to say. Okay, so you're going to use the following reagents. So you'd use NaOET, followed by propyl bromide, and then our third step, H3O plus and heat. We're going to decarboxylate one of the two esters and turn it into a carboxylic acid. And from here, we're adding the amount of carbons that we added to our chain here. Because there are two different protons, we could technically do this twice. We're going to walk through this one a little more stepwise. So NaOET, let's go ethyl bromide. We do this again, NaOET. Let's go butyl bromide. And then lastly, H3O plus is going to make both of these into carboxylic acids, and we're going to lose. Well, I usually just try losing the left one. Doesn't really matter if you lose the right one. It's the same concept. So we'll end up with one carboxylic acid. We need our ethyl group. And then we need our 4-carbon butyl group, giving us this compound here. It looks a little messy. Let's draw it all out in one big equation so you guys can see what that would look like. So this is the exact same thing we just did below, just kind of condense it down into one long 5-step equation here. First step, we're going to add the ethyl bromide. Second step, well, first 2 steps, ethyl bromide. Steps 3, 4, add butyl bromide. And the last one, you're going to make your carboxylic acid. All right. We can also do something called the acetoacetic acid synthesis. Sorry. Acetoacetic ester synthesis, which is going to be very similar. We're just going to delete one of these esters. Oops. And replace it with a ketone. And it's going to do essentially the exact same thing. So if instead of malonic acid or diethyl malonate, if we take ethyl acetoacetate, which is going to look like this here. The real difference is in our last step where we could hypothetically have decarboxylated either of these two esters. We're only really going to be able to decarboxylate this one. So it's going to simplify our process a little bit. Actually, you know what? So exact same concept. NaOET. Propyl bromide gives us to a propyl addition here. If we add an H3O plus and heat, we're going to be able to decarboxylate this left portion of our molecule. And be left with just a ketone in this case. We can also do this in 2 steps like we could the other one, or at double alkylation like we could the other one. So let's draw something up. All right, so I'm gonna draw through this a little bit stepwise. After step 1 and 2, we're gonna get this molecule. After 3 and 4, we'd get this, and then after decarboxylation for step 5, we could get to here. Yes, I'm sorry. All right. One more part of chapter 21 to talk about. We're going to do some Michael additions. So Michael additions deal with what are referred to as alpha beta unsaturated ketones, which are a ketone with a double bond next to it. There's 2 different things that can happen. So if you add a Grignard to these, they kind of just do a normal reaction. Grignard. Grignard is going to come in and attack at the carbonyl center. We're going to end up making an alcohol. Plus this ethyl group. We kind of ignore the double bond in this case. If we add in a cuprate, it's going to do the extended addition. And this is what most molecules are going to do when they attack this. So instead, they're going to do what's referred to as the Michael addition. So if we add in ethyl, Cuprate here, it's going to instead attack. Draw this out. Our extended position. This can then come down, pick up an H plus from water, H3O plus. And give us what you think of as like a 1,4 addition. You're adding further away into your kind of extended system and then reprotonating to keep your ketone. So this is what's called a Michael addition. We can do them with a couple of different things. So you can do them with a cuprate. You can also do them with a diester. We take NaOH. Throw in our alpha beta unsaturated ketone, followed by H3O plus. We're able to initially deprotonate. From here, we can attack our, oh, sorry, it's H3O plus. Michael acceptor. This stuff. And then the last step, we're going to have this proton come down, pick this up, or sorry, the electrons come down, reform our ketone, pick up this proton. And do this Michael addition here. So there is another reaction we can do with this, where instead we do this whole thing in base and heat. And instead of stopping here, we can go onto a second reaction. So we're going to talk through that. So this is referred to as a Robinson annihilation. It is going to consist of two parts. We're going to have a Michael addition followed by an aldol condensation. The reagents for it are just going to be NaOH, and our alpha beta unsaturated ketone. You can add them all in together. You don't need any 1 or 2 steps. And then lastly, we're going to need heat. So what we're going to have happen is we're going to pull off a proton. From here, we're going to do a Michael addition. Pick up that proton again. This is where things are going to get kind of interesting. We're set up at this point to do an aldol condensation. So if we pull off this proton here with NaOH that we have in solution, we can have it come in, attack, make a 6-membered ring. This is, we'll draw these out a couple times. From here, going to do our condensation. So we're going to pull off our OH, or sorry, pull off our H, mega double bond. Our OH can grab the other proton to give us our final product. I'm going to give you guys a minute to get caught up. So methyl number 1 is here, methyl number 2 is here. So these are a little bit like a Diels-Alder in the fact that they always kind of form the same structure. So let's look at a really simple one and then look at a more complicated one and talk about where things are coming from. So this is our simplest form of it. It's going to give us just a 2-ring structure. These always form a 6-membered ring with a double bond that is located here. This is our general structure for this reaction. It'll always occur like this. If we make a 5-membered ring for the starting material, the only difference is that this left ring is now 5-membered. Like so. Let's start adding some more carbons to it and talk about where those carbons go. So I'm going to go back to a 6-membered ring, add a carbon here, put 2 more carbons on this end. If I look at my molecule, this carbon here corresponded to this carbon here. So I've extended that chain. All we're going to do is add some more carbons to that position. So we have the 1 carbon from our ring here. We added 2 more carbons than normal to this position. So it's going to extend this by 2 carbons here. Let's take a look at the top example. I'm just going to kind of add some things to it. So if I added 2 more carbons on both ends here, throw an ethyl group here. So our general structure is the same. We need that ethyl group. Now, let's go back down to this little one. This on the right corresponds to this position, which means if we added an ethyl group here, we need 2 more carbons in this position. Adding an ethyl here adds 2 more carbons to this position. So they look like big, scary reactions, but in fact, they all kind of always do the same thing, which makes them a little bit less intimidating. I'm going to cover one more reaction in this chapter, then we'll take a little bit of a break and talk through 22 and some synthesis problems. Chapter 22 is really short. We've already learned almost every single reaction in it. All right, so the last thing we're talking about is the Stork enamine synthesis. So up till now, we've been using these diketones for everything. If we want to try to use a monoketone, we're going to run into an issue where it's a little bit too basic. So what we need to do is use an enamine as an intermediate. So essentially, we throw this in solution, add, I don't know, LDA. This is our desired product, but it doesn't really work. Instead, it just kind of acts as a base and pulls off one of these protons or just something stupid, and it just doesn't work. So instead, we are going to make an enamine. So adding in a large hindered secondary amine. Can get us to here, and then from this point, if we throw in our Michael acceptor, followed by H3O plus, we can both kind of kill two birds with one stone here. We're going to get rid of the imine or the imine here, as well as protonate our ketone to give us there our desired product from these reactions. So they're a bit odd looking. But they're doing the exact same basic concept we've been doing before. So taking a regular ketone, some sort of secondary amine followed by our Michael acceptor, H3O plus, lets us do a normal Michael addition. Extramethyl next to the ring, this one here. Okay, so we're attacking essentially make a negative here. We attack at this position, which means that there is still another methyl here that's just kind of floating off. So that methyl correlates to this one here. All right. Let's take about a 10-minute break. Come back here at 10:10. We're going to quickly go through chapter 22. And then we'll do a little bit of synthesis and call it. So I'll see you guys in about 9 minutes. All right, chapter 22. Which is all about amines. So, ways to make amines. We know a bunch of them. We can take bromoalkane, throw in NaCN to make a nitrile. Followed by LAH. And water lets us turn this into amine. Some other ways, we can do it through an amide. Taking a carboxylic acid, throwing in initially SOCl2 to make the acid chloride, followed by ammonia. And then LAH let us reduce this. Some other ones, if we have like a nitrile and an aromatic ring, throwing in FeHCl, lets us make an amine here. We also know how to make it through imines. So taking a ketone, throwing in some sort of amine, primary, secondary, doesn't really matter. Can give us an imine here, followed by LAH or H2 in platinum. Can give us amines here. Some other ways to make amines. So our nitrile method has a little bit of a problem to it where it's going to add an extra carbon. So we're starting with propyl bromide and ending with butylamine. If we want to do this without adding any carbons to it, there are two different ways we can do this. We can either do this through an azide, which is very similar to a nitrile. So if we instead add NaN3, so NaCN would be this, or we could add Na sodium azide or sodium azide, depending on how you pronounce it. And what this is going to do is the exact same thing. It's going to do an SN2. From here, throwing in LAH will let us reduce off N2. So we're going to lose 2 of these nitrogens and be left with just, in this case, propylamine. So we don't have that issue we had before where we're adding extra carbon. Now we're just directly making an amine from our bromide here. The other way we can do this is through what's called a Gabriel synthesis. We're going to take a reagent called phthalimide. All right. Nope. Add in potassium hydroxide. It's going to deprotonate the amide. From here, we can attack propylbromide. And then if we add in hydrazine, we are able to do a double displacement. We're going to kick off this group here to form our amine. So it looks pretty complicated. Really, you're taking propylbromide, adding in phthalimide and hydrazine to get an amine here. So it looks complicated, but the actual process is pretty straightforward, starting with propylbromide, ending with propylamine. Amines themselves are pretty good nucleophiles. So if we take this propylamine here and throw in some methyl iodide, these can do nucleophilic attacks. They're pretty easy to derivatize. Another equivalent of your propyl or propylamine can pull off a proton here. And you can add methyl groups to this. You can do this a couple times in a row if you want. Eventually, if you add enough at base, you can add 4 of these. What's in this chapter? All right, so that's 22. Pretty straightforward chapter. And we learned 1, maybe 2 new reactions in it. So most of it was a review. Your only real new concepts Br, NaCN, followed by LaOH, no, LAH, and water. Gonna make a carbon extended amine. You can instead add NaN3 followed by LAH. Let's get 2. And water. You can do your direct amine conversion. So you're not adding an extra carbon for this one. Or alternatively, we can go through a Gabriel synthesis. Followed by hydrazine. To get to the same product here. Adding in some sort of nucleophile with an iodine on it will let you derivatize your amine, and you can do it as many times as you really want, up to 4 substituents off your amine. Cool. All right, let's do some synthesis problems, and then we will be done with material for the class. So I'm going to put up a synthesis problem, give you guys a little bit of time to kind of think through it. and see what you guys come up with. So my hint's going to be that you're going to do some sort of Robinson annulation for these. You're going to have to figure out a way to set yourself up for it. Oh, I know. So I'm going to give you guys about, let's say, till 10:35 to try to do this reaction, do this synthesis. And then I'm going to draw out a second one for you guys to work through. If you get done with the first one, feel free to hop on the second one. All right, so let's start with this first one. All right, let's kind of think about this backwards a little bit. We need to do some sort of Robinson annulation. So we're going to need to set ourselves up with product of our Robinson annulation is going to look something like this here, which would come from something like these components. And with this in mind, we can kind of construct our synthesis around this. We need to get here, do this reaction, and then do some sort of transformations to get to our final product. So getting to our first kind of intermediate should be pretty straightforward. We just need to oxidize it. We could do either oxidize and compound. They'll both get us to the right product. So either PCC or chromic acid, because they're secondary, doesn't matter. From this point, we need to add in our Michael acceptor. There's nothing really going on either of these areas, so we don't need any extra carbons on our molecule. This is going to give us our normal Robinson product. From here, we need alcohols instead of ketones, so we need to reduce this. We also don't have our alkene here, so we're probably going to want to reduce this as H2. That's going to get rid of absolutely every bond, double bond here. H. This is going to get us really close to our final product. From here, we're just doing a normal Williamson ether synthesis. So we can throw in NaH to pull off our protons on our alcohols, followed by methyl iodide to make ethers. All right, so I'm going to redraw that second one, give you guys a little bit of time to work through that one. I'll give you guys till about 46 to work through it. We'll talk through it as a class and then call it for the day. I can leave that up for a second. Erase some of this portion of it. So most likely we're going to be doing some sort of Claisen condensation in order to get our 6-membered ring. If we're taking a look at this, if we deprotonate here, we'd have 1, 2, 3, 4, 5, 6. So it makes sense that we start out with something like that. If we throw in our Na OET, we're going to be able to make our general skeleton. From here, taking a look at this, we've got ethyl groups coming off of everywhere we had a carbonyl. So if we throw in excess Grignard, we'll be able to trialkylate. And then we just need to get rid of these alcohols to get to our final product. So a couple of different options. We could throw in H2SO4 to do the E2. We're going to make kind of chaotic double bonds, but it doesn't matter because we're going to get rid of them in the next step. So I'm going to kind of put them in some spots they could go. And then H2 is going to get rid of all of them. Okay, so that's a few examples of synthesis problems. I've got a couple more I'm going to post as like a extra synthesis problem like I did for the last chapter. Tomorrow we will maybe go through a few more synthesis problems as well as go through the previous exam 4s. So that is all the material in the class. I will see you guys tomorrow for review day. So have a good Tuesday.